Hello all of you. Welcome to the 55th lecture of the course on analysis and modeling in chemical engineering. In this week, we have been discussing about computational methods of solving separation problems. We first began with equilibrium based methods and we discussed different approaches like BP method, SR method, NR method, inside out method and so on. And then in the last class, we started discussing about how we can incorporate the non-equilibrium effects in the separation problems by doing, first we discussed about using the tray efficiency, but then we said that it is not quite efficient and adequate for many circumstances. So therefore, we have to think about an alternative strategy, and then we had the formalism of a rate based method. The fundamental idea in the rate based method is we include the effect of the mass and heat transfer between the vapor and liquid phases, right. In the equilibrium methods, we assume that the vapor and liquid is in equilibrium, so there is no net mass transfer between vapor and liquid and no net heat transfer between vapor and liquid, right. But in the rate based methods, we relax that assumption, right. So we have a non-equilibrium stage where there can be a mass and heat transfer between the liquid phase and vapor phase. And we developed these equations called MERS HQ equations. The M equations correspond to the material balance for the vapor and liquid phases, E equation for the energy balance of the vapor and liquid phase, the equation correspond to the mass transfer rates, S equations for the summation of mole fractions at the interface, H equations which is kind of optional. This was the hydraulic equation for the stage pressure drop, and finally we had the phase equilibrium relations at the vapor liquid interface, right, which are the Q equations. Keep in mind that this nomenclature is very different from the mesh equation nomenclature, right. Let us say for example, E referred to phase equilibria in mesh equation, but now it is referring to the energy balance equations. And we have of course more equations in the rate based method compared to the equilibrium method that we have discussed. Okay, so these were the final set of equations that we had, the M equations both for liquid and vapor for every component in every stage. Then we had the total material balance for the liquid and vapor in every stage. Then we had the energy balance for the liquid and vapor and also at the interface. Then we had the equation for the mass transfer rates in liquid and vapor. Then we had summation equation. Then we had equations for pressure drop. And finally, we had the equation of phase equilibrium at the interface. Again, phase equilibrium is assumed only at the interface, not everywhere else, right. All right. So, let us look at the first term, the first thing here, that is the mass transfer within an unequilibrium stage, right. So, we had introduced net mass transfer rate Nij in our equations, Nijl and Nijv for the liquid, which has to come from this mass transfer rate equation. And if we think about it, this mass transfer rate is going to basically consist of two components. The one component is because of the diffusion and the other component is because of the bulk flow. What exactly we mean by this, right? So, let us say for example, if you have a mixture of A and B, right. So, now there is a possibility that A can move relative to B, where A is moving in a particular direction and B is moving in a particular direction. So, this is my kind of a relative movement, or A and B can move together, right. And of course, at the molecular level the movement is always random, but just to convey the idea of what do we mean by bulk flow, right. This is a bulk movement, right. So, it may so happen that the entire mixture is moving together in a certain direction because of, let us say, a flow, then all the components are moving along with the flow. That is what I mean by the bulk flow. The other thing is that one species, because of whatever reason, is moving relative to the other species, that is my diffusion, right. The diffusive flux is defined typically as J, right, written typically as J, right, and we have to multiply the flux with the corresponding area to get the net mass transfer rate because of diffusion. The bulk flow, this is my bulk mass transfer rate, right, and this has to be multiplied by the mole fraction of a species, because bulk always means the entire mixture. So, if I multiply with the mole fraction of the particular component, I get the movement of that component because of bulk flow in the system, right. So, the flux for the net mass transfer rate for component I in stage J is therefore given as sum of these two, and we can define it both for the vapor phase and the liquid phase. AJI is my total interfacial area that we have in the stage. So, between this, because the mass transfer takes place through this interface, right, and then this Jij, as I said, is my molar diffusion flux, right. Diffusion flux can be defined with respect to a mass average velocity or a molar average velocity. Since we are working in moles here, so we will define relative to the molar average velocity. It is always relative, diffusion is always relative. So, there has to be a reference to this. So, we can take a reference as the mass average velocity or the molar average velocity. We are taking the reference as the molar average velocity. Okay. For a binary mixture, the situation is somewhat straightforward. The diffusive flux for component I can be defined as something like this. CTV is the total molar concentration. This multiplied by the difference of the mole fraction of the component I at the vapor and at the interface, right. This multiplied by this basically gives me the concentration difference for the species I, right, because Ct into YIV gives me the concentration of I in the vapor phase, and CTV into YII is the concentration at the interface, right. So, I am trying to show that by this picture. This is my vapor phase, this is my liquid phase, here is my interface, right, and then we have some mole fraction defined at the interface for component I, and there is a diffusive motion from the bulk of the vapor towards the interface, and this will happen because of the concentration difference CIV and CII, and the concentration will be defined as CTV into YIV, and this will be CT V into YII. Now, clearly this will not be same at everywhere in the stage, right, because stage is going to have good amount of vapor, and it need not be always like uniformly present, right. Since it is non-equilibrium anyway, the composition can also vary quite a bit, right, and also it can vary with time. So, therefore, we need to define some kind of an average, right. So, this is the average concentration difference in the vapor and liquid, vapor and the vapor interface, right. Same thing we can do for component I in the liquid phase. So, from the interface, let us say it is going in this direction. So, we have a liquid phase mole fraction at the interface and going to the bulk liquid, right. In the way that we have shown, we have taken the positive direction of mass transfer from the vapor to the liquid phase. That means, we are assuming that the flow is taking place for component I from the vapor to the liquid. In case the flow is happening in the opposite direction, we can simply have a negative value of the flux J, right, that is all. Now, we have the total concentration in the liquid and vapor, that is why I say CTP, where P can be L or V. This K values that we have here, these are my mass transfer coefficient, again based on the mole fraction driving force, right. The driving force again also I can define in terms of the difference in, let us say, mass fraction, right? But we are defining with the mole fraction. We are also defining the J with respect to the molar average velocity. So this is the mass transfer coefficient also based on the mole fraction driving force, and typically it has to be computed experimentally anyway, right? And these ones, as I said, is the mean driving force because of the mole fraction difference. And as I said, I can always express it in terms of the concentration difference. So mole fraction difference multiplied by the total concentration gives me the concentration difference, which is my driving force, right? And now finally, if I sum up all these J's, since J is anyway a relative flux of component I with respect to the other, they should sum up to 0, right? So for example, for 1, J1 is relative to species 2, that is the movement of or transfer of 1 relative to 2. J2 is opposite of that, the movement of 2 relative to 1, right? So therefore, if 2 is moving with some velocity with respect to 1, then 1 is also moving negative of that velocity, right, with respect to 2, right? So that's why J1 should be equal to minus J2, right? So it works beautifully for a binary mixture, but then as we go for a ternary mixture and so on, things start to become bad. In fact, even this picture is not completely correct, as we have discussed in the beginning of the classes, right? This concentration gradient is not always the driving force, right? And I have given examples of situations where the concentration difference does not lead to a mass transfer, right? And the celebrated example is of oil and water. So if oil and water are together, there is a concentration difference of oil between the oil and water phase. This oil phase is plenty in oil, water phase has pretty much no oil. So there is a huge concentration driving force for the mass transfer of oil from oil to water phase, but it is not happening because oil and water are immiscible, right? So the concentration difference is not explaining the mass transfer here, which is not taking place, right? So then we said that the actual reason is not the concentration difference, it is the chemical potential gradient which is present there. It so happens that for the case of, let us say, binary mixture, it so happens that if the two components are miscible and all that, then the concentration difference may drive mass transfer, but it is not a general rule. It is only true for a specific situation where the components are miscible or they are in the gas phase and so on, right? Let us say the example of a smoke. It is going in the air and it is a perfect example of the application of Fick's law. Here the concentration gradient is driving the mass transfer, and here for oil and water it does not, right? And therefore, as we just said, we have defined chemical potential gradient as the actual driving force for the mass transfer. For example, if you have two phases 1 and 2, then if the chemical potential of A in phase 2 is higher than phase 1, then A will go from phase 2 to phase 1, and vice versa for the component 1 if the chemical potential of 1 is higher than chemical potential of B in phase 1 is higher than chemical potential of B in phase 2. And in fact, we said that this will continue until we reach equilibrium, and at equilibrium these differences are going to vanish. And in fact, this is what gave me the E equations in the original mesh equations for equilibrium stage. So we have taken chemical potential equality, and then we wrote that in terms of fugacity first, and then in terms of partial fugacity coefficients, right? And finally, we had the notion of the k value, and we got something like yi is equal to ki xi from chemical potential equality, right? But now, since we are looking at non-equilibrium effects, we are basically departing from that assumption of chemical potential equality. Now the chemical potential difference is actually giving me a mass transfer, and it is that mass transfer rate that should be actually considered as opposed to a concentration difference. That is the first thing that we have to keep in mind. It may so happen that in the case that you are doing, that the chemical potential gradient, when you have put that thing inside the equation, will give you something similar to this for the binary mixture, but it is not always true. It is true for gases and all that, but not always true. Okay. The second thing to keep in mind is that you may not have a binary mixture, you may have a ternary mixture, let's say. Now, let's say you have three components, 1, 2, and 3. Now, I can define the movement of 1 relative to 2, the movement of 1 relative to 3, and I can define the movement of 3 relative to 2. So, now we can define all this different kinds of movements which are possible in the system with respect to the different components which are present in the system, and all of that has to be considered within our framework, right? And then there is also going to be some kind of like coupling between the components, which is referred as the pair coefficients or the binary pair coefficients. The general name for that is the Maxwell-Stephen mass transfer coefficient, right? So, here I am doing the same thing for basically 3 component system, but we have defined for 1 and 2. The third one I can get from the fact that the total sum of all the diffusive fluxes will still be 0, right? So, but if I do for only the component 1 and 2, you see now we have 2 terms for component 1 and 2. The first term is 1 moving through 1. So, 1 is also moving through other 1 species, then other is 1 moving through 2, the third is 2 moving through 1, and fourth is 2 moving through 2, right? The general idea of diffusivity is defined like that, right? So, when you have a pure component system, that may also diffuse, right? But that will be the diffusion of the same molecule through a system containing same molecules, right? That is something that we have in my K11 here. But then if you have a binary mixture, then or a ternary mixture and so on, then the component can move with respect to other components. So, we have a notion of a mutual diffusivity, and we will have so many of the mutual diffusivities possible because every component can move with respect to every other component in the system, and that has to be accounted for. So, the general form for a multi-component mixture is therefore going to be quite complicated. We will going to have some sort of a matrix. We will write it only for the first C minus 1 components. The last component anyway we can get from the fact that the summation of the j's are 0 for every stage, right. So, it is going to look like something like this. That may look like some sort of a general form for what we had in the binary case, right. But then this j is now a vector, a column vector of length C minus 1, because we are writing the relative flux for all the components in there in the vapor phase. Then the total concentration, that is a scalar in the vapor. Then we have a matrix containing C minus 1 into C minus 1 terms, right, and this is going to now consist of these pair coefficients, which are loosely related to the notion of the mutual diffusivities that you have, or the Maxwell-Stephen diffusivity. In principle, the framework is quite involved and you can read about it, but I am giving you a basic feel of what is going in there. And then again, instead of this y1 minus y1v minus yiv minus yi1 that we had, now we have a general column vector like this, let us say I am writing it for this case, my kappa matrix will look like kappa 1 1, kappa 1 2, kappa 2 1, kappa 2 2, all for the vapor, and my y vector is going to look like y1v minus y1i and y2v minus y2i, and my j vector is going to look like j1v and j2v, and I can still write this equation as something like j is equal to CTV and then multiplied with this kappa and into this y, which is, in our case, I can also write it as something like yv minus yi, where then I define two different column vectors. Yv is going to be y1v, y2v, and yi is going to be y1i, y2, right? In addition to this, we are now doing it for also for the liquid phase. So this matrix actually will get quite complicated and involved, but the fundamental idea remains the same, that the flux is given as total concentration multiplied by a matrix containing the binary pair coefficients that tells me how one component moves with respect to the other, multiplied by the average mole fraction difference that we have there, right? And then we have kind of a system of equations to basically go around, right? The next thing that we did is, as I said, we need to basically look at not the concentration gradient, we have to look at chemical potential gradient, and therefore we need to somehow include thermodynamic information somewhere in our framework. And where can we include it? We can include it in this kappa matrix, right? So what we say is that if we have an ideal gas, then this kappa is some R matrix, where this R can be written as something like this. There is a derivation for this I am not getting into. This R can be written as this, the terms of R can be something like this. That totally depends on the mole fractions only, right? So the component II is given as the mole fraction of I, Zi, overall mole fraction, divided by the mass transfer coefficient for component C. Keep in mind that I am doing it for a C by C C minus 1 into C minus 1 matrix. So I am not doing it for the Cth component, right? So I am doing it only for the C minus 1. So therefore, the IC is coming separately here, and then I have a sum over the others, right? And then we have something similar for the terms other than the diagonal terms, right? And again, there is a detailed derivation for this, but this is true only for the ideal gas. If we have a non-ideal liquid solution, then we are going to multiply this quantity, which depends only on the mole fractions. Of course, we have mass transfer coefficients, but other than that, only depends on the mole fraction, into another matrix, which is basically going to correct for non-ideality that I am having. And where this gamma matrix comes from? This gamma matrix will come from something like this, where I have my notion of activity coefficient, right? Typically, we consider the liquid to be in the non-ideal state, and we assume that the vapor is ideal. In that case, for the liquid, we introduce the notion of activity coefficient and so on, which is more convenient for liquid, as we have discussed. So therefore, the expression gamma that you see here, that is including this activity coefficient, right? But in principle, we can also include a similar term for the vapor, maybe in terms of fugacity coefficients, right? So this is the general framework that we can follow to basically account for the mass transfer effects. Next is my heat transfer effects. The heat transfer is also going to consist of basically two terms. One is my convective heat transfer. The first term is because of the temperature difference, right? Again, we have an interfacial area that is coming in there, and then there is a heat transfer coefficient similar to the mass transfer coefficient that we had here. Now we have a heat transfer coefficient appearing in the energy heat transfer equation, and then we also have another contribution because of the bulk flow, and that is in terms of the partial molar enthalpies of all the species and the sum over the component mass transfer rates, right? And we can do it for both the liquid phase and the vapor phase, right? So once we have this, we can go ahead and solve these equations, and there are softwares that can do that. One of the two most common softwares are this ChemSep software that has this rate based methods incorporated, but it is also there in Aspen, and they can also handle this rate based methods, and they have all the selection of methods that can be incorporated in addition to the equilibrium based methods. Of course, it is going to be computationally more involved compared to the equilibrium based methods, but in some cases where the equilibrium assumption is far from real, in that case we do have to go for the rate based model. So with that, I conclude my discussion on the separation processes modeling, and this week of the discussion on the computational methods that is applied to separation problems, particularly vapor liquid cascades that are found in distillation problems and absorption and stripping problems. And then therefore we have more or less concluded the discussion on the process modeling part of this course. That is, we have first discussed like reactors, then evaporators, and now we have done separators. In the next week, we are going to discuss the recent trends that we have in the process modeling, right? So with that, I conclude this week of lectures. Thank you so much.